when we're working with inhomogeneous systems, which is to say when the constant vector b is not the zero vector, things are a little bit more complicated, but thankfully they're not that much more complicated. A lot of what we do for the homogeneous system still applies. Let's say we're trying to solve the system AX equals B, where specifically A is the same coefficient matrix as before, but B is the non-zero constant vector 10, 3, 4. So, all right, so now we put this together in an augmented matrix, and we have to sort of try to reduce the matrix to get at least an echelon form, or even potentially a reduced row echelon form. Turns out that exactly the same operations will work and will produce the row echelon form that we're looking for. Now, the only thing that changes here is what's happening with constant vector. So if we apply the operations row 3 minus row 1 to row 3, we also have to apply it to the term on the right of the vertical line, right? 4 minus 10 is minus 6. So we don't have 0, 0, 0 here anymore. If you go through this process, you will find that the augmented matrix still has 2 parameters. It is still a consistent system. We don't have a bunch of zeros and a 1. That was sort of lucky, although that was, set up that way. But it's conceivable that when we go through this, we might have gotten something like a 1 here, in which case there would have been no solution. But that's not what we have. It turns out that we do get a 0. So we have 2 leading variables, 2 parameters, and so there's going to be infinitely many solutions. But it isn't going to be a vector space or a subspace, the set of solutions, because it is not going to be going through the origin. We used exactly the same operations as when we solved the homogeneous system with the same coefficient matrix. When we write the general solution, which is to say, let's say that this is S, this is T, then we would have x1 plus S plus T is equal to 4. Then we take, again, all the S's and the T's and we send them to the other side. So we get x1 is equal to 4 minus S minus T. And we get that x2 is equal to 3 minus S plus 2T. You put all the constant terms together. You put all of the S terms together, you put all of the T terms together, and you end up with, well, something that looks like a span of 3 vectors, but it isn't a span, right? Because this isn't full on all the possible linear combinations. You're looking at the linear combinations of these 3 vectors where the first vector is there exactly once. The rest of it, if you were to break it down, separate it into that vector plus the span of the rest, then that's your regular thing. Now, we write this, and because it's like a nice way to sort of view this, basically the solution is that subspace plus this special solution, which we call the particular solution x0, and if we solve the system and we find the RREF, that's always going to be the same. It's like the equivalent of the basic solutions, but for the constant term here. But I mean, it's not clear what it means to add a vector, which is x0, to a subspace. Like, we know what it means. It means that every vector in the subspace, we end up adding it to 4, 3, 0, 0, the particular solution. But it's just when we write plus here, you got to think about what it might mean. So geometrically, what it means is that we translate, which is to say we move the subspace null space of A away from the origin by that specific particular solution to get the solution set of the inhomogeneous system. So if you have the solutions for the homogeneous system and you have a particular solution, then you have the general solution of an inhomogeneous system. Those of you who study differential equations, you're going to see something of a similar nature when you look at different methods to solve inhomogeneous differential equations. There's a link between linear algebra and differential equations, but you'll see that when you study differential equations. So let's say you had a system ax equals b which was consistent, so you at least have one solution. If you have a particular solution x naught or x0 right here, and v is a solution of the homogeneous system, then x0, the particular solution, plus v, basic solution or solution of the homogeneous system, is a solution of the inhomogeneous system. So it's just formalizing what we said before. In order to get a solution to an inhomogeneous system, you find a particular solution, and then you find all the solutions of the homogeneous system, and you add those together. And if you have two solutions to the inhomogeneous system, then subtracting one from the other actually gives you a solution of the homogeneous system. That tells us that basically the general solution of an inhomogeneous system is exactly a solution of the homogeneous system. Sorry, I wrote by V here. What do you mean? By x0 plus solutions of the homogeneous system. How do we prove this? Well, it's quite straightforward. If x0 is a particular solution, then you know that a times x0 is equal to b. That's what it means to be a solution. And let's say that v is a solution of the homogeneous system, then you have a v is equal to 0. So if you look at x0 plus v, a times x0 plus v will be, by distributivity of matrix product, ax0 plus a times v, ax0 by assumption is b, and av by assumption is 0. So we have b plus 0, that's b. In the other case, ax0 is equal to b, that's the assumption. ax1 is equal to b as well, also the assumption. So if I look at a of x0 minus x1, that gives me a of x0 minus a at x1, again by the distributivity of the matrix product, which is ax0 minus ax1, b minus b, which is 0. That gives us a pretty good idea as to what the solutions of inhomogeneous systems are. If your homogeneous system has a unique solution, then anytime you build an inhomogeneous system that is consistent with the same coefficient matrix A, that system will also have a unique solution. But it has to be consistent. It might not be. If your homogeneous system has infinitely many solutions, and perhaps you have k basic solutions, so k parameters, then assuming that you create an inhomogeneous system which is consistent with the same coefficient matrix, that system will have a general solution also with k parameters. So you also have infinitely many solutions. But all of this is useless unless we happen to have access to a particular solution x0 of an inhomogeneous system. And often we can do that by guessing, or we might have some prior knowledge of a situation. That's never a bad thing. But the theorem doesn't help us solve the system. It just tells us that the nature of the solutions are the same. not going to be subspaces because you're adding the particular solution and you're not going through the origin anymore. But if you have 2 parameters, you have 2 parameters. If you have 1 parameter, you have 1 parameter. If you have a unique solution, you have a unique solution, assuming the system AX equals B is consistent. Well, what does it mean to be consistent? The constant vector B has to be in the column space of A, right? Because we saw that A times X is a linear combination of the columns of A. And if B is not in the column space of A, then AX equals B cannot have a solution because A times X cannot be written as B. B is not a linear combination of the columns of A. So if that's the case, there's no solution, and knowing null space of A doesn't actually do anything. So, in summary, here's a theorem which we'll leave as an exercise. We'll assume that it's been proven and we can use these things, unless you're told specifically not to use this theorem or the statements. But if you have an m by n matrix A and you take a vector x which is in Rn, so it has as many entries as A has columns, then all of these things are the same statement. If one of them is true, they're all true for A. If an x, if one of them is false or one of them doesn't apply, then none of them apply for A and X. The system is consistent for all constant vectors B if and only if the rank of the matrix A is M. In particular, you have a leading one in every single row. So you cannot have a degenerate row in the reduced row echelon form of the augmented system. The RREF doesn't have a 0 row. Every row has a leading one. If and only if every vector in Rm, seen as a constant vector, it's a linear combination of the columns of A, if and only if the column space of A is the entirety of Rm, and if and only if the dimension of the column space of A is M. So we'll leave that as an exercise, but by now that should be clear if you've understood all the concepts we talked about so far. Here's a second theorem. Here we're talking about the system specifically, right? So if A is an n by n matrix, X is a vector in n space, then the system AX equals B has a unique solution for all B, as opposed to it's consistent. So we're talking about unique solutions. Unique solution, every variable is a leading variable. There's a leading one in every column. That's important. The columns of A are linearly independent, the null space of A is 0, and the rank of A is n. When I say the null space of A is 0, I mean it's the 0 subspace.